What is a nucleophile, right? So a nucleophile is going to be, let's say it's A, is going to be an atom that is not very nice with electrophiles, or well, they don't really like electrons, okay? So they're gonna have like a negative outlook on their lives, right? They don't like electrophiles, or I should say they don't like electrons. So you can really tell if something is a nucleophile if it has a negative charge. So this A has a negative charge. That means it's going to have an excess amount of electrons, right? So let's say we have some electrons right there. And we have so many electrons that were so negative and so depressed that we can just give them away, right? And an electrophile is something that really loves electrons. It really loves electrons. So we're going to have B, and it is going to have a positive charge. Now, an electrophiles, here's a mnemonic, have a positive outlook. So they really love electrons, right? So whenever a nucleophile and an electrophile meet, the nucleophile will actually donate some of its depression to the electrophile, right? And so what we will have is an acid-base reaction, or specifically a Lewis acid and a Lewis base. So we now have A and B. B is going to have some negative, right? And A is going to have this right here, and right there. Now we're neutral, and this is going to be also neutral. So negative and a positive cancel out. Usually for the MCAT, if you're going to be taking it, if not, it's a good thing to know. Whenever you see a carbon with a plus, or nitrogen with a plus, or oxygen, or fluorine, whatever, these are going to be your electrophiles. Whenever you have carbon with a negative, nitrogen negative, oxygen negative, fluorine with a negative, these are going to be your what? Your nucleophiles, right? And you're going to be seeing them a lot on the test, or just in organic chemistry. Just make sure you look out for them. The main difference between a Lewis acid and a Lewis base and just normal Bronsted-Lowry bases and acids is that a Bronsted-Lowry only refers to hydrogen. So Bronsted, right? Whatever, however you spell it, refers only to hydrogens, right? So, for instance, you would have what? An OH negative reacting with some water, right? It would react. You would end up getting H2O and then another OH, right? That would be like the product. And in this case, this is acting as what? Well, we're accepting something, so this is going to be acting as the base. This is going to be acting as the acid. And notice that there was a transfer of a proton. If someone says a proton, they're really just talking about a hydrogen. They're just being obnoxious, right? So it's just like a proton transfer. Lewis acids and Lewis bases don't have to deal with hydrogen. They're actually dealing with the electrons themselves, right? So that's the main difference. For instance, in the case of A negative and B positive, there are no hydrogens involved. However, there is a transfer of electrons, and that's what makes us so different, right? That's what makes us so different. Okay, so Lewis involves lone, right? L, lone pairs, and then Bronsted, right? Involves hydrogen. And so that's the main tidbit that you should be looking out for. That's really about it for Lewis acids and bases with nucleophiles and electrophiles. So now you know that nucleophiles tend to have a negative outlook on their life, so they're negative, and electrophiles are good. They're lovers. Loving is good, so therefore they're positives, right? So that's all you need to know. So for this problem, I want you to rank from 1 to 4, 1 being the highest and 4 being the lowest, the most acidic molecule. So to do this kind of problem, you need to actually have the anion, right? So we're going to actually deprotonate, we're going to take away a hydrogen. So let's end up doing that. We will have, let's do this in a different color, we will have NH2 minus. And whenever you have one of these long branching chains, right, I recommend just drawing out the Lewis structure right here. So let's do that. We have a CH3, which we know to be like this, connected to a carbon that has 2 hydrogens, and that is connected to an oxygen with a hydrogen. So now we're going to deprotonate it. We're going to take away that hydrogen, right? And that oxygen will become negative. You can check the formal charge. That's going to be negative. We will have CH3 attached to a carbon that is double bonded to an oxygen that has another oxygen that has a hydrogen. And then we're going to take away that hydrogen because we're deprotonating. We're taking away hydrogens because it's an acid. And that becomes negative, right? Okay. And then we will have just CO. All right. So now let's draw out the line structure. That's a carbon attached to a carbon attached to an oxygen. That's negative. We have a carbon attached to another carbon that's double bonded to an oxygen, and that's bonded to an oxygen. That's negative. And we just bring these down. So CO, negative, and H2, negative. So which one is more acidic? Well, if you know your acids, you would know that this is number 1. But why is that? Why? Well, it comes down to electronegativity. When you're doing these problems, here's the priority you should be doing. Priorities. It should be electronegativity, right? Well, actually, yeah, it should be electronegativity, and then it should be like bonds, right? So, as you know, if you follow the trends, we have CNOF with the chlorine right here, and we increase electronegativity going towards chlorine all the way right there. And now you're probably wondering, why does that matter? Well, electronegativity means that we're more actively trying to incorporate electrons. We're trying to gather electrons more. And so that makes us more acidic. We want to have more electrons, right? Therefore, chlorine is going to be the most electronegativity or electronegative out of all these molecules. Nitrogen is right here. It's less electronegative than oxygen, and oxygen is less electronegative than chlorine. Therefore, chlorine is going to be number 1. It's going to be number 1 right here, right? So it is number 1, acidic. And now we're going to move down the line. So we're done with this row, right? Check mark. We're going to go down here. So we don't go to nitrogen. No, we go directly to oxygen, all right? But notice that we have 2 oxygens. We have 2 oxygens. And which one do you think is going to be more electronegative, or the more stable, right? It's going to be this one. But why is that? Well, think about it. Yeah, it has more bonds, but it also has resonance. You see, resonance, I'm just going to call it res, it actually increases stability, right? And so the more stable acid is equal to strong acid, right? And so we can actually make another structure and that's a resonance structure, right? So therefore this molecule has 2 resonance structures, meaning that it's super stable and will act as a great acid. Yes, this has an oxygen that's negative, but you can't make another resonance structure because there's no oxygen right here, right? And therefore, it's not going to be as good of an acid, but it's pretty good when you compare it to nitrogen. And of course, nitrogen is going to be like the worst one out of the whole bunch, right? It's the least electronegative out of the whole pair, and it doesn't have any resonance to it. It's the least electronegative, but you should really be going through those priority groups. So really, it should be electronegativity, resonance, and then bonds. So this is like the previous problem. I just want you to rank the acidity. Whenever you're doing this, think anions. So we're just going to be stripping off a hydrogen. We're going to rewrite these structures like this. That's an oxygen, make that negative. That's another oxygen, make that negative. For this one, I recommend that you actually write out your electrons, right? So that one would have 2 electrons right there. So let's see. Whoa. Nitrogen with hydrogen. Oop. Right there. So that would make it what? Negative, right? Because 5 minus 4 is 1. 1 minus 2 is -1. And for this one, this is kind of special, right? Very complicated. Just make that a negative, right? Because you're just taking away an invisible hydrogen. Again, it should be what? Electronegativity, let's just call that En. So it should be electronegativity. And then what? Resonance and bonds. Okay, cool. Well, if we're going through electronegativity, I'm going to be ignoring nitrogen, I'm going to be ignoring carbon because oxygen is more electronegative than those two. Alright, so what about these two? Well, they both have oxygens, so we can't use the electronegativity. But what about resonance? Well, this one can actually form a resonance structure, right? An oxygen, make that negative. Okay? So notice that that negative actually moved 1, 2 spaces, right? So that's just another trick that you can use to make sure that your resonance makes sense. Our bond moved 1, and then our negative moved 2 molecules. Cool. Alright, so this one cannot form resonance, meaning it's not as good, it's not as stable because stability raises acidity. Alright, so that's going to be number 1. Let's write that in red. It's going to be number 1. Well, oxygen is more electronegative than nitrogen and more electronegative than carbon, so that's going to be number 2. Nitrogen is more electronegative than carbon, is number 3, and carbon's the worst, is 4. If I wanted you to rank this in basicity, the more stronger an acid we are, the weaker we are as a base. So we're going to have strong acid is equal to a weak base, and a weak acid is equal to a strong base. So number 1 is going to be number 4 for our bases, right? This is going to be number 1 because it's the weakest acid, meaning it's going to be the strongest base. So 4 is going to be 3 and 2. Okay? So it's in the opposite direction. I know it's a bit confusing when you're doing it like that, but trust me, it evens out. It works perfectly. So the stronger the acid you are, the weaker of a base you are. The weaker of an acid you are, the stronger of a base that you become. Okay? So just memorize that. It's more of a concept. We're not using pKa.